You know when you see those incredible factory robots moving with perfect timing, and you just have to wonder, how do they know exactly what to do every single time? Well, in this explainer, we're going to pull back the curtain on the world of robot languages and programming. We'll break down how we talk to these machines, from the most basic movements all the way up to some really complex, intelligent tasks. So let's start with that big question, right? How do you get a robot to perform a task not just once, but millions of times with almost flawless precision? Well, the answer is all in the programming, and that's exactly what we're going to unpack right now. All right, so here's our game plan. First, we'll define what robot languages actually are. Then, we'll trace their evolution through four pretty distinct generations. After that, we'll look at the different ways you can get a program into a robot, compare the super important online versus offline methods, and finally, we'll take apart a simple robot program to see how it all fits together. Let's jump in. First up, what even are robot languages? We're going to focus on how we communicate with robots using text, kind of like how a software developer writes code for an app on your phone. So a textual robot language is pretty much what it sounds like. It's a language where we used typed out commands to tell a robot what to do. But it's not just about movement, go here, go there. It also covers the logic for making decisions and reacting to what its sensors are telling it. And this is why they're so vital in industry. They give you the flexibility and precision you need for the really complicated jobs. Okay, let's look at a few of the big names you'll run into. First, there's VAL. It's one of the originals, really known for its simple syntax for just moving from one point to another. Then you've got something like AML, which is a much more powerful, high-level language, great for handling tricky data. And a more modern example is Rapid from ABB. It's a real workhorse out there for things like welding and assembly. Now that we have a feel for what these languages are, let's take a look at how they've evolved. It's a pretty cool story, actually. We're going to walk through 4 generations that take us from just telling a robot where to go to having it actually think for itself. The first generation languages, they were all about one thing, motion. You'd use some basic text commands along with a thing called a teach pendant. It's basically a handheld controller to set up your points. Perfect for simple, repetitive stuff. But generation 2, well, that was a huge leap. The game changer was adding intelligence. Suddenly, you had structured languages that let the robot use sensors and even talk to other computers. And this idea of a robot feeling its world is what's really fascinating here. Think about a gripper. A Gen 1 robot could just open or close it. That's it. But a Gen 2 robot? It could use a force sensor to pick up an egg with just the right amount of delicate pressure so it doesn't break. That's not just an upgrade. That's a whole new ballgame. So that brings us to the third generation, what we call task-level languages. Here, the whole mindset shifted. Instead of programming every single tiny movement, the programmer just defines the overall task. You tell the robot what to do, like assemble this gearbox, and the system is smart enough to figure out how. And Generation 4? That's where we're headed now. It's all about full-on AI, where the robot can learn, reason, and adapt all on its own. And this right here is where all of this is leading. The whole idea of world modeling is a cornerstone of what's next. Imagine the robot has a perfect 3D model of its entire workspace stored in its memory, kind of like a map in a video game. With that, you can just give it a high-level goal, and it can figure out its own path and all the steps to get it done. Okay, so we know about the languages, but how do we actually get the program into the robot? Well, there are really 2 main ways to go about it. You can physically show the robot what to do, or you can write out all the instructions in code. These teach-by-showing methods are called lead-through programming. In powered lead-through, a programmer uses that handheld control box, the teach pendant, to drive the robot to each key point in a sequence. But with manual lead-through, it's way more hands-on. You literally grab the robot's arm and physically guide it through the exact motion you want it to do. And believe it or not, powered lead-through is the most common method you'll find in factories today. It's perfect for those point-to-point tasks, like picking something up from over here and putting it down over there. You just use the pendant to define point A and point B, and the robot will remember that path and play it back perfectly millions of times. Manual lead-through, sometimes called the walkthrough method, is for jobs that need a really smooth, continuous motion. Think about spray painting a car door or laying down a perfect weld seam. You need a fluid, curvy path, and the best way to get that is to just do the motion yourself and have the robot record your every move. Okay, next up is a really practical question, something that factory managers have to deal with all the time. Where does the programming actually happen? Do you do it right there on the production line, or can you do it somewhere else? This is the whole debate between online and offline programming. And you can see the trade-offs pretty clearly here. Online programming, with the Teach Pendant is simpler. But, and this is a huge but, you have to stop production to do it. The robot isn't working, and that's expensive downtime. Offline programming lets you write and test everything on a computer without ever stopping the robot. So while it might take a bit more setup, it can save you a ton of invaluable production time. All right, let's put all these pieces together and actually look under the hood at what the code inside a robot program looks like. We're going to deconstruct the basic commands that make the robot move and get things done. So here are some of your fundamental building blocks. You've got move P1, which is pretty straightforward, right? It's a direct order. Move the arm to the point we've called P1. Then there's approach, which is a little more clever. It tells the robot to approach a point from a certain distance. And of course, you've got a command like speed to control just how fast the tool is moving. Now, let's see how we can stack these simple commands together to perform one of the most common, most essential robot tasks out there, a simple pick and place operation. And this flowchart lays out the logic perfectly. The program starts, the robot moves to its home position, and then it goes to the pick location. The command close I1 tells the gripper to close and grab the object. Then it moves over to the place location. Open I1 tells the gripper to open up and release it, and the cycle is done. It's a really simple, elegant flow, all built from those basic command blocks we just talked about. So we've gone on this whole journey, right? From literally pushing a robot's arm around by hand to writing complex code, all the way to a future where robots can basically program themselves. We've watched these languages evolve from simple commands into complex, AI-driven systems. And it leaves us with this final thought. As robots get truly good at learning on their own, what's going to be the next big, meaningful task that we decide to teach